You can continue, sir. Recording is started. Selvakumar, sir.
Okay, sir. Good students. So in this session, yes, sir. Hello.
Yes, sir. You are audible. You can continue.
So in this session, we are going to discuss about digital logic gates, answers, the problems given in the previous session. So in the previous session, we have discussed about methods to represent signed binary numbers, signed magnitude representation, and signed ones complement and signed twos complement. Then we also discussed about extension, contraction, and saturation of binary numbers. And we have discussed arithmetic operation of signed binary numbers. So based on that, we have given two exercises in the last session. So the solutions are here. So you can verify the answers here with your answers. So the first exercise given in the last session is what are all the numbers can be represented with 4-bit in the given representation, also represent it. Okay. So in the first column, the numbers are given plus 12, minus 16, plus 7, and minus 8. In second, third, and fourth columns, respective representations are listed. So you can represent plus 7 in all the three representations because it is a positive number. It is possible to represent this plus 7 in all the three representations. Okay. But what about plus 12 and minus 16? You can look at the question. We have to represent the number in 4-bit manner. Okay. So in case of 4-bit manner, you can only represent up to minus 7 to plus 7. Okay. In case of sign magnitude representation. So plus 12 minus 16. These two numbers are not possible to represent in 4-bit manner. Right? Then minus 8. Minus 8 can be represented in only signed twos complement representation. We cannot represent minus 8 in signed magnitude representation and signed ones complement representation. Okay. Then the corresponding data. So how we can represent the plus 7 and minus 7? So this is the answer. So since it's plus 7 is a positive number, signed magnitude representation having the digits like 0, 1, 1, 1. Similarly, signed ones complement and signed twos complement also represented with same bits 0, 1, 1, 1. Okay. So minus 8 can be represented in signed twos complement only. So the signed twos complement representation of the negative number minus 8 is 1, 0, 0, 0. Okay, so this is the answer. Please note it down. Then the second exercise, the signed binary arithmetic operation. So based on this topic, we have given problems. So the first one is perform the addition of the signed numbers plus 65 and plus 36 represented in signed twos complement form. Okay. Then similarly, there are three other problems. So two addition problems, then two subtraction problems. The corresponding answers are here. So you can also check it out whether the answer found by you is correct or not. So with this, we will start digital logic gates. So we have a familiarity on this logic gates because in high schools we have studied about these logic gates, AND gate, OR gate, NOT gate, like that. Okay, so same logic gates are only discussed here elaborately. So like your electric and electronic circuits, what are the basic components are used to construct we can use to draw the circuit, or what are the components we will use to construct these kind of circuits? What are the basic components we will use? You can give your answer in chat box.
You kindly type it in the chat. WhatsApp asking.
Ram sir?
I asked them to type, sir.
Okay,
What
sir.
the basic logic gates, you know. Kindly type it in the chat, students. NAND, NOR. Okay, Jivita, and or not, she is typing, sir. Then
Not
we
bad.
have
But
Divya Priya, and
my
not.
question was,
Okay.
what are the basic components used for constructing the electric and electronic circuits? So in the previous semester, we have studied electric circuits and electronic devices and circuits, right? So in these courses, we have used basic components or devices to construct electronic circuits or electric circuits. So what are the components?
Hello, Kumar, sir, your voice is not audible. Hello, Kumar, sir, your voice is not audible for us.
Sound. Hello? Sir, கேக்குதுங்களா?
Yes, sir, you can continue. Now
How
we are
audible,
able
sir?
to hear your voice.
Hello?
Yes, sir, now we are able to hear you.
Voice கேட்கல. Hello? Ram sir?
Yes, sir, we can able to hear you. You can continue, sir. Hello, Kumar, sir. Yes, students, I think some technical issue there. Okay, we will wait for some time. Theobala typed resistance, switch, diode, transistor, capacitor, inductor. Okay, Jivita typed resistor, transistor, capacitor, inductors. Srihari typed transistors, diode, resistor, capacitor, etc. Very good. You remember those components you have used in electronic devices lab. It's very happy for us. So similarly, in digital electronics lab, we are going to use the digital logic gates. Okay, logic ICs. What you have told earlier, you have mentioned many logic gates. Among that, the basic logic gates are AND, OR, and NOT gate. Okay, AND gate, OR gate, and NOT gate. Okay, so these are the basic logic gates. Okay, wait, I will present.
Yes. Hello, sir. Hello.
Presentation start. Hello, Kumar sir.
Sir, கேக்குதா? Hello.
Yes, sir. எப்போட கேக்குது?
Hello, Ram sir. Ram sir.
Ajit sir, can you hear me?
Yes, sir. Sir, you just continue, sir.
Is the slide is visible?
Yes, sir, visible.
Okay, dear students, in this session we are going to discuss about the digital logic gates. So already in your high schools, you have heard about the digital logic gates. So what are the fundamental logic gates we are having? Before we are going to discuss that, we should know what is digital logic gate. Okay. So digital logic gates are basic building block of digital electronic circuit. To build any digital electronic circuit, we have to use the logic gate. So what is the logic gate is? It's an electronic device which accepts one or more digital input. Selvakumar sir, at least audio mute பண்ணி வைங்க Selvakumar sir. Selvakumar sir, kindly mute the audio. Mukund sir, audio mute பண்ணி வைங்க phoneல. Okay, digital electronic gate is an electronic device which accepts one or more digital inputs and produces a digital output based on the logical operation. We will know what is meant by logical operation in the later session. Okay, so what are the arithmetic operation we have performed so far? Addition, subtraction, multiplication, and division. Those are arithmetic operation. But here the logic gates are used to perform the logical operation. Okay, the basic logic gates we are having are AND gate. Okay, the basic logical operations we are having are AND operation, OR operation, NOT operation. Okay, so three basic logical operations we are having. They are AND, OR, and NOT operation. There are some other logical operations which can be derived from the basic operation and are NAND operation, NOR operation, exclusive OR. It can be also termed as XOR or simply XOR. Similarly, exclusive NOR or XNOR or simply XNOR. See, you kindly note down the representation for exclusive OR and XNOR. In our material, we are going to use only simply XOR for exclusive OR and XNOR for exclusive NOR operation. Kindly make a note of it. Okay, so NAND operation is nothing but the NOT of AND operation, inverse. AND operation result நம்ம invert பண்ணோம், not பண்ணோம் அப்படின்னா we will be getting NAND operation. Similarly, NOR operation, the inverse of the OR operation, we can term it as NOR operation. Then exclusive OR and exclusive NOR are different operations which are the combination of AND, NOT and OR. இதெல்லாம் mix ஆகி நமக்கு இதுல வரும். Fine. The logic gates are, all the logic gates are available to perform these operations. That means AND, OR, NOT, NAND, NOR, exclusive NOR, இது எல்லாத்தையும் perform பண்றதுக்கு we have ICs available. Okay, each IC can have up to four logic gates. Say for example, I am going with AND gate IC, means I can have 4 AND gates. Okay, similarly for OR gate. In the case of NOT gate, we will be having 6, that we call it as hex inverter IC, like that. Fine. So these are the different gates available in the form of IC: AND gate, OR gate, NOT gate, NAND, NOR, XOR, XNOR. In this AND, OR, NOT, these 3 gates we call it as basic gates. Okay, the remaining are derived from the logical operation of the basic gates. Clear? In this NAND gate and NOR gate, particularly NAND gate and NOR gate, can be called as universal gate. These 2 gates we can call it as universal gate. Am I audible, sir? Sumi ma'am, am I audible? Okay.
Yes, sir, audible.
And NOR
Audible.
as universal gates. Kindly make a note of it. We will know the answer in the later sessions. Okay, why NAND gate and NOR gate are called as universal gate? Later class la adha paakalam. Okay, so what are the basic gates? AND gate, OR gate, and NOT gate. What are the derived logic operations? NAND, NOR, XOR, and XNOR. What are the universal gates we are having? NAND and NOR gate. Okay, we will know the reason later. If anybody know the answer, you can kindly type it in the chat box. Okay, the NAND gate and NOR gate, we call it as universal gate. If you know the answer, you can type it in the chat box. Any idea? It performs action of all other gates. Rizwan, very good. Actually, using NAND gate and NOR gate, we can implement the other logical operation. Say for example, AND, OR, NOT, XOR, and XNOR using NAND and NOR gate. That's why it is termed as universal gate. In most of the digital circuit, all the operations are carried out by this gates only. That's why it is called as universal gate. Okay. The AND gate operation can be derived from using NAND gates itself. Okay, now we have to know what are the symbols we are going to use for the logical operation. So we are having the operation AND operation. The symbol is dot. Okay, whenever we are having a dot in an expression, it indicates it's a AND operation. OR operation, we are going to use plus symbol for the OR operation. Please remember one thing, even though we are saying plus, it doesn't mean addition. இது நல்லா ஞாபகம் வச்சுக்கோங்க. Plus symbol நம்ம யூஸ் பண்றோம் அப்படின்னா லாஜிக்கல் ஆபரேஷன் பொறுத்த வரைக்கும் என்ன மீனிங்? OR operation அப்படின்னு மீனிங். It doesn't mean addition operation. Okay, then NOT operation. NOT operation can be represented by a bar or a dash symbol. என்னோட வேரியபிளுக்கு மேல நான் என்ன பண்ணுவேன், ஒரு கோடு போட்டிருந்தேன் அப்படின்னா அது வந்து என்னது? NOT operation. Or simply we can have a single quote at the end of the variable. ஒரு quote மட்டும் நம்ம போட்டிருக்கோம் end of the variable அப்படின்னா it is also termed as NOT operation. We can also say NOT operation as ones complement. நம்ம கொடுக்கிற டேட்டா என்னவோ அதை அப்படியே இன்வெர்ட் பண்ணி கொடுக்கிறது தான் NOT operation. ஓகே, அதோட சிம்பிள் தான் இங்க நம்ம மென்ஷன் பண்ணியிருக்கோம். இன்வர்ஸ் ஆஃப் வேரியபிள் a அப்படின்னா a bar அப்படின்னு சொல்லலாம், இல்ல a single quote we can put. Fine. Now XOR operation சொன்னோம்னா as a plus symbol enclosed in a circle, that we call it as XOR operation. அதோட சிம்பிள் தான் இங்க நம்ம போட்டிருக்கோம். Similarly for XNOR, a dot within a circle. Okay, a dot within a circle is the symbol for XNOR operation. Fine. So these are the symbols we are going to use for the logical operations. Okay, in most of the expression we are going to use only the basic logical operations. Say for example and or not, இதனோட symbols தான் boolean expression. Later we will discuss. அதுல எங்க பார்த்தாலும் அதுதான் யூஸ் பண்ணும். Fine. For NAND and NOR operation there is no specific operator symbol because it can be represented by and, not of and. Okay, NAND can be represented as not of and operation பண்ணிட்டு அதுக்கு மேல ஒரு பார் போட்டோம் அப்படின்னா அது NAND operation. That's it. Similarly NOR operation, you have to perform OR operation, then if you put a bar over it, okay, it is termed as NOR operation. So these are the symbols we are going to discuss now. AND gate அப்படின்னு சொன்னோம்னா அதோட சிம்பிள் வந்து இதுதான். Clear? This is the symbol for AND gate, this is the symbol for OR gate, and this is the symbol for NOT gate. Before I am going to move to the next slide, you can take a snapshot when I am saying. Okay, fine. So AND gate அப்படின்னு சொன்னோம்னா என்ன பண்றோம், அதுக்கு ரெண்டு இன்புட் இங்க இருக்குது, ஒரு அவுட்புட் இருக்கு. We can have many number of inputs, but we have only one output in the case of AND gate. Okay, so இங்க நம்ம எக்ஸாம்பிள் கொடுத்திருக்கிறது 2 input AND gate. You can also have 3 input or 4 input like that. Okay, the expression is C is equal to A and B. What I am saying, C is equal to A and B. A and B means AND operator is dot. As I mentioned earlier, A dot B, that is A and B, logically ANDed the value of A and B. Okay, next OR gate, the two inputs are A and B. As like for the AND gate, the output is C. Can you type it in the chat box? What about the expression for the OR gate? Can you type it in the chat? Am I audible? AND operation க்கு நான் expression எழுதிட்டேன். Yes, very good.
Audible.
Shalini, very good. Jayavardhini, very good. Jeevita, very good. See, kindly interact. Okay, see, today we have some technical issue as we tried to present it from the college campus. Okay, so I am continuing, so don't lose your interest on the class. Okay, kindly listen to the class and answer it. Okay, I'm very happy many of you answered C is equal to A plus B. Yes, that's right. C is equal to A or B. When we are pronouncing, we have to say A or B. Like that only we have to say. Fine. Similarly, for NOT gate, what is the expression? For NOT gate, we will be going to have only one input and one output. In the case of AND gate or OR gate, multiple inputs we can have and we have only one output. In the case of NOT gate, we are having single input and single output. Can anyone type the expression for NOT gate? You cannot able to put bar over your variable. You can use single quote at the end of the variable. C is equal to what? Jivita, y equal to x bar you put, it's correct. But here the variables are A and C. C is the output variable, A is the input variable. Divya Priya, you have Sivabala, A equal to C, that's wrong. C is equal to A bar is the correct answer. C is equal to A bar is the correct answer. You can write it like this, or you can put C is equal to A, one single quote also you can put. Okay, C is equal to A bar. Fine. Now, இங்கே நம்ம பார்க்கிறோம் and அப்படினா மீனிங் என்ன? A and B அப்படினா மீனிங் என்ன? Both A and B. Simply we can say both A and B. A, B, OR gate. That means OR operation means A or B. What we can say? Either A or B. That's the meaning for that. Is it clear? AND gate na enna sonnom? Both A and B. OR gate na enna sonnom? Either A or B. C is equal to either A or B. Here C is equal to both A and B. That means A and B. Here we are saying either A or B. In the terms மட்டும் ஞாபகம் வச்சுக்கோங்க. When we are seeing about the truth table and the logic operations, you can clearly understand what I am saying. The NOT operation you all know. Invert of A or complement of A. That's it. Kindly take a screenshot of this. This screenshot எடுத்து வச்சுக்கோங்க. Later நீங்க படிச்சுக்கலாம். Okay. Shall we proceed to the next slide? Kindly take a snapshot of this. Okay, we will move to the next slide. So NAND gate, this is the symbol. You can clearly see one thing. What is the difference between the symbol of AND gate and NAND gate? You can type it in the chat box. The symbol of AND gate and NAND gate. I will show it the previous table. This is the symbol for AND gate. This is the symbol for NAND gate. Yes, there is a bubble. This one is typing O. Okay, that means there is a bubble. There is a small circle we are putting before the output pin. Okay, in the output side, we are having a small circle that we call it as bubble. Which represents invert of AND operation. That's why it is called as NAND. Okay, not of AND gate. That's why it is termed as NAND. Similarly, NOR gate, what we are having? Yes, Dinesh Kumar saying it is a combination of AND gate and the NOR gate. Very good. Okay. Whereas in the case of NOR gate, it is the combination of OR gate and NOT gate. See, na AND gate in series with NOT gate போடுறதும் NAND gate ஒண்ணுதான். Similarly, for NOR gate, OR gate in series with NOT, அதோட equivalent தான் என்னது? NOR gate. You are having a IC itself to perform the NOR operation. So அதனால அதுக்கு ஒரு symbol assign பண்ணியிருக்கிறாங்க. Fine. Next.
Excuse me, Ram sir. Ram sir.
Yes sir, Gajan sir, it is audible.
Okay, you continue, sir. You continue. We will come back.
Okay. So for XOR gate, we are putting a line before the OR gate. You can see it. A curved line before the OR gate. See, like this, you can remember the symbol for all the gates. No need to get confused. You just remember the symbol for AND or NOT. Okay. AND gate oda end la na or circle pota adu NAND gate. OR gate oda end la or circle pota na adu enadhu NOR gate. If I put a curved line before the OR gate, it is simply XOR gate. That's it. Clear? Here, A, B are the inputs and C is the output. Here the expression is C is equal to A dot B whole bar. Kindly make a note of it. AND operation means A dot B. Okay, NAND operation means I am complementing the output of A and B. That's why I am putting a whole bar. It is not A bar dot B bar. Please kindly note it carefully. C is equal to A dot B whole bar. This where எப்படி represent பண்ணலாம்ன்றது I will type it in the chat box. Kindly make a note of it. You can also represent like this. Chat box la type பண்ணிருக்கோம் பாருங்க. C is equal to bracket la என்ன பண்ணிருக்கோம்? A dot B. அதுக்கு அப்புறம் என்ன பண்ணிருக்கோம்? ஒரு single quote போட்டுருக்கோம். Like this also you can represent. Similarly, NOR gate, C is equal to A plus B the whole bar. When we are pronouncing, we will say it as a plus b whole bar, but it doesn't mean addition. Okay, a r with b and its complement. Okay, that's the meaning for that. Yes, Dinesh Kumar typed C equal to a plus b whole bar. Very good, Dinesh Kumar. Okay, then for XOR gate, C is equal to A XOR B. This is the symbol for XOR. Already I have told you C is equal to A XOR B is the expression. See, in the expressions ellame ஞாபகம் வச்சுக்கணும், because Boolean equation, when I am converting it into a digital logic circuit, you have to interpret the symbol and its expression. என்னோட எக்ஸ்பிரஷன்ல நான் எழுதி இருக்கிறத சர்க்யூட்டா ரெப்ரசென்ட் பண்றதோ இல்ல சர்க்யூட்டை எக்ஸ்பிரஷனா எழுதுறதோ நமக்கு தெரியணும். then only we can able to implement it. Okay, is it clear? So okay, a XOR b அப்படினா மீனிங் என்ன அப்படினு பார்க்கலாங்களா? எக்ஸ்க்ளூசிவ் ஆர் அப்படினா மீனிங் என்ன? any idea? எக்ஸ்க்ளூசிவ் அப்படினா மீனிங் என்ன? எக்ஸ்க்ளூசிவ் ஆர், if both the inputs are exclusive means, exclusive or means either A மட்டும் இருக்கணும் இல்ல B மட்டும் இருக்கணும். ஓகேவா? ஆர் கேட்ல அப்படி கிடையாது. at least A or B. Okay, sorry, I used either A or B, that is wrong. at least A or B. Okay, in the case of OR gate, இங்க எனக்கு XOR கேட்ல either A or B, that is the answer. Okay, either A or B. அதை எப்படி ரெப்ரசென்ட் பண்ணலாம்னு பார்க்கலாங்களா? Fine. You can also represent the XOR. You can also express the XOR operation like this. A bar dot B. இதுல எது மட்டும் எனக்கு லாஜிக் ஹை, B மட்டும் லாஜிக். Either B or A. அப்ப மீனிங் என்ன? A இருக்கக்கூடாது, B மட்டும் இருக்கணும். அப்படி இல்லைன்னா என்ன இருக்கணும்? A மட்டும் இருக்கணும், B இருக்கக்கூடாது. That is the meaning. இந்த expressions நோட் பண்ணி வச்சுக்கோங்க. Kindly take a screenshot. Then we will proceed to the next slide. Okay, then we will proceed to the next slide. XOR க்கு இது ஞாபகம் வச்சுக்கணும்ப்பா. A bar B plus A B bar is the expression for XOR operation. First இதுல வந்து பாத்தீங்கன்னா ஒரு எக்ஸ்பிரஷன் என்ன போட்டுருக்கோம் பாருங்க, A bar dot B. அப்படின்னா மீனிங் என்ன? இதுல B மட்டும் தான் எனக்கு வேலிட், A வந்து பார்னு போட்டுருக்கோம் காம்ப்ளிமெண்ட். அப்ப இது இருந்தா அது கிடையாது, இது இருந்தா அது கிடையாது. So A dot B bar அப்படின்னு போட்டுருக்கோம். So this is the expression for XOR. Shall we proceed to the next slide? Am I audible?
Yes, sir. Audible, sir.
Okay. Now XNOR. XNOR அப்படின்றப்ப நம்ம என்ன பண்றோம்? Just we are putting a bubble symbol before the output. Okay. So XNOR அப்படின்னு சொன்னோம்னா XOR ஓட invert. That is the meaning for XNOR. So it can be like this. A XNOR B. The operator symbol is dot enclosed in a circle. That's why we have written like this. இதுக்கு மீனிங் என்ன அப்படின்னு பாத்தீங்கன்னா A B, A bar B bar plus A dot B. This is the meaning for XNOR operation. Okay, இதுக்கு மீனிங் என்ன அப்படின்னு பாத்தீங்கன்னா ரெண்டுமே ஒரே லாஜிக்ல இருக்கணும். That means ரெண்டுமே 0 இருக்கலாம் இல்ல ரெண்டுமே 1 இருக்கலாம். அப்படி இருந்தா மட்டும்தான் அவுட்புட் 1 வரும். That's the meaning for the XNOR gate operation. So இதுல kindly நோட் பண்ண வேண்டியது எது? நமக்கு ஞாபகம் வச்சுக்க வேண்டியது எந்தெந்த கேட்? Kindly type it in the chat box. What is the expression for XOR gate? Kindly type it in the chat box. Expression for XOR gate. Expression for XOR gate. Kindly type it in the chat box. Expression for XOR gate. Expression for XOR gate. Kindly type it in the chat box. Am I audible?
Yes, sir.
Yes, Rizwan is typing. Mugun sir, சொல்லுங்க முகுந்த் சார். கேக்குது.
Not clear, sir.
Okay.
Sir, Rizwan and Soumya Ravi typed for exclusive or representation,
Very
sir.
good, very good, very good. It's correct. Rizwan and Soumya, you have typed correctly. Very good. Is it clear now? XR அப்படின்னு சொன்னோம்னா A bar B plus AB bar. இது எப்படி ப்ரொனவுன்ஸ் பண்ணலாம்னா A dash B plus AB dash அப்படின்னு சொல்லலாம். Okay. For XNOR, it is like this. A bar B dot B bar plus AB. Okay. So இதுல ஒரே ஒரு விஷயம் மட்டும் பார்த்துக்கணும். AB whole bar கிடையாது. A bar dot B bar plus A dot B. Fine. So these are the symbols and expression for all the logic gates. We hope already you have come across these things. Hello Kumar sir or Mugun sir, kindly mute your mobile. Okay. So things we must remember. Okay, it's very, very important. Don't forget it hereafter. The operator symbol plus denotes logical OR operation. It doesn't mean addition operation. That you have to remember. The operator symbol dot denotes logical AND operation. It doesn't mean multiplication operation. நீங்க அங்க பார்த்த arithmetic operations-ஐயும் logical operations-ஐயும் confuse பண்ணிக்க கூடாது. Boolean expression அப்படின்னு நம்ம ஒன்னு பார்க்க போறோம். Full and full அதுல நம்ம யூஸ் பண்ண போறது என்னது? Logical operations only. Logical operations only. Then operator symbol single quote போடலாம், அப்படி இல்லைன்னா மேல ஒரு பார் போடலாம். This denotes logical NOT operation, which is nothing but one's complement of the particular variable. One's complement of the particular variable. That's it. So இந்த மூணு பாயிண்ட்டை வந்து ரிமெம்பர் பண்ணிக்கோங்க, மறந்துடக்கூடாது. பிளஸ் போட்டிருக்கு சார், அப்ப A plus B அப்படின்னா ரெண்டுத்தையும் ஆட் பண்ணுமா? இட்ஸ் நாட் லைக் தட். ஓகே, இந்த லாஜிக்கல் ஆபரேஷன்ஸ் எல்லாமே நெக்ஸ்ட் வரக்கூடிய ஸ்லைட்ஸ்ல we are going to discuss. Fine. Okay. Shall we proceed to next slide?
Ram sir.
சொல்லுங்க செல்வகுமார் சார்.
Shall I continue?
எஸ் சார். ஸ்லைட் நம்பர் 18ல இருந்து கண்டினியூ பண்ணுங்க.
சரிங்க சார். Hello.
Yes sir, we can hear you.
Okay sir. Okay, so still now we have discussed the symbol used for logical operations and logical gates. Okay, so hereafter we are going to discuss about how these logic gates are operating. So logical operation of logic gates. So first we will start with AND gate. So the concept behind this AND gate is, if only all the inputs of AND gate is logic 1, then the output is logic 1. Okay. If it is a 2-input AND gate, both the inputs should be logified. Then only this AND gate will produce logic 1 output. Otherwise, the output will be 0. Okay. Or alternatively, you can say that if one of the input is logic 0, the output should be logic 0. Right? So this is the truth table representation of logical operation of AND gate. Okay, so here we will use a new concept that is called truth table. So in this truth table, what we will do? So in this truth table, actually it is a table. This table consists of the possible inputs and corresponding outputs. Okay, so this table describes the operation of any gate, right? So the truth table provides all the possible combination of inputs and its corresponding output for any digital electronic circuit. Okay, not only for logic gate, it is also includes digital circuits, right? So here we are going to see about logical operation of AND gate. So we know that here we are dealing with 2-input logic gates. So that means 2-input AND gate. So the 2 inputs are A and B. So on these 2 logic inputs, when you are performing AND operation, then you will get logical expression like this: C equal to A dot B. So these are things we have discussed in the previous slides. So based on that, here you can also observe that there are two inputs. If inputs are two, then what are the possible combinations? How many possible combinations are there for two inputs?
They are typing 4, sir.
Okay.
Rizwan typed 4. Very good, Rizwan.
Yes, good. So, for example, if I am taking a coin, okay, taking a coin and tossing. So, what are the possible results are there? There are two possible results. One is head, another one is tail. For one coin, two possibilities. If you are taking two coins, four possibilities. Like that, here the inputs are two, so possible combinations are four. Okay. So here we are having AND gate. For this AND gate, we are giving two inputs that are A and B. If I am giving inputs like logic 0, okay, both the inputs are logic 0, then AND operation will give logic 0 as an output, right? If I am giving logic 1 on the input B, then what should be the output? Again, the output is 0. Then the third combination, if I am giving logic 1 on the input A, but the input B is logic 0, then again the output is logic 0. Okay. If I am making both the inputs, input A and B, both are logical 1, then my output goes to logic 1. Right? So it is similar to a series connector of switch. If I am taking two switches, okay, which are connected in series. So like this. Okay, here I am connecting a lamp, or for example, for simplicity, I am taking LED. So here I am connecting a DC source. Okay, this is my supply. Then these are my two switches, controlling switches. Okay, this circuit is for understanding the operation of AND gate. Okay, so I'm taking example circuit to make clear on the operation of AND gate. Okay, so here we have two switches that are A and B. If I am closing the switch A only, what will happen? Then the status of LED is off, right? Because two switches are connected in series. If the switch A is closed, then B is open. Then what will happen? There is no closing path in the circuit. So there is no current flow through the circuit. Then LED will be off, right? Then again, if I am opening the switch A and closing the switch B. If I am closing the switch B, but the switch A is open. For this condition, what will happen? Again, there is an open circuit. So still the LED is off. But if I am closing the switch A and B, now both the switches are closed. Then we can observe that there is a closed path. So through this closed path, we can observe the current flow. So LED will turn on. Okay, for this condition only, the LED will be turned on. Okay, like that. If both the switches are closed, that means we are applying logical 1 on both the inputs. The case 4. Okay, fourth case in this truth table. So if both the switches are closed, that means for AND gate, we are applying logical 1 on both the inputs. Under this condition only, AND gate will be turned on. For other three cases, the lamp or the output of AND gate will be logic 0. Okay, is it clear? Is there any doubt on this logical operation of AND gate?
No, sir.
Okay. Then we will move on to the next gate, OR gate. Okay. Still, here also we are assuming two input OR gate. So the logical operation is if at least any one of the input of OR gate is logic 1, then output is logic 1. Okay, at least any one of the input is logic 1, then the output of OR gate should be logic 1. Okay, otherwise the output will be 0. Right? So this is the truth table for OR gate. Here we are again considering two inputs A and B. This is the logical expression for OR gate. Okay, so here the first combination is 0 0. When you are applying 0 0, then you will get a result, that is output of OR gate is 0. Okay, when I am applying the input combination 0 and 1, that means input A is 0, input B is 1. Okay, for this condition, for this combination of input, the output of OR gate is logical 1. Okay, then the third case, logic 1 is applied on the input A and logic 0 is applied on the input B. For this condition also, we are getting logic 1 in the output. Okay, in the fourth combination 1 1. We are applying logic 1 on both the inputs. For this combination also, OR gate produces logic 1. Okay, so here you can observe that these three conditions. Okay, any one of the, at least any one of the input is logic 1. Okay, here in the second case, input B is logic 1. So one input is logic 1. So output goes to logic high. Okay, similarly in third case, input A is logic 1. Okay, even though input B is 0, this gate produces logic 1 in the output. Right? In fourth case, both the inputs are logic 1. Okay, both are logic 1. So this gate produces logic 1 in the output. But what about the first case? Both the inputs are 0. Okay, for this condition, OR gate produces logic 0 as the output. Right? So for OR gate, at least any one of the inputs should be logic high. Then only OR gate will produce output as logic 1. Otherwise, the output should be logic 0. Okay, is it clear? Then, another gate, the logic operation of NOT gate. So, NOT gate is nothing but an inverter. It is a single input gate. Okay, single input gate. In case of AND gate or gate, these two gates at least have two inputs. Okay, A and B. But in case of NOT gate, this gate only having one input and one output. Okay, so if the input of the NOT gate is logic 0, then output will be logic 1. Okay, the reverse of the logic level. If you are applying logic 0 on the input, then you will get logic 1 on the output. If you are applying logic 1 in the input, then you will get logic 0 on the output. Okay, so this is the inverting operation or NOT operation. Okay, so this gate is denoted as NOT gate or named as NOT gate. Okay, so this is the truth table for NOT gate. Here we are having only one input, that is input A. Okay, we are taking output as C, right? So here the output, the logical expression for this NOT gate is C equal to A bar. Okay, A bar or A complement. Okay, that means complement of the input. So if you are applying logic 0 in the input A, then output will be logic 1. Okay, if you are applying logic 0 on this input A, then this NOT gate will produce logic 1 as the output. Okay, so because of logic high in the output, then this lamp will be glowing. Okay, then the second case, logic 1 is applied on the input A. For this case, the output will be logic 0. Okay, so here we have only two combinations because this NOT gate having single input. If it is a single input, there are only two possible combinations. Okay, 0 and 1. Hello? கேக்குதுங்க சொல்லுங்க யார் Okay, so next one, the logical operation of NAND gate. So in this slide, we are going to discuss about operation of NAND gate. So here you can observe that the NAND gate is complement of AND gate. Okay, so we have discussed in the AND gate operation in the previous slide. So after discussing this slide, you can observe that the NAND operation is inverted of AND operation, right? So NAND operation is the NOT of AND operation, or you can say AND followed by NOT gate, AND followed by NOT gate. Okay, so here we are having two inputs. Okay, still this gate also having two inputs, A and B. Okay, so this is your AND gate, then this is your NOT gate. Okay, by combining these two gates, then you can realize NAND gate. Okay, this is my output C. Right? So if all the inputs, one second. So if all the inputs of NAND gate is logic 1, then the output is logic 0. Okay, if all the input of NAND gate is logic 1, then the output is logic 0. Okay, otherwise the output will be logic 1. So this is the truth table for NAND gate. Here you can observe the logical expression for NAND gate. Okay, so A dot B, this alone AND operation. Among this AND operation, we are complement operation or NOT operation. A dot B whole bar, A dot B whole bar. So this is the logical expression for NAND gate. Okay, so here we are having two inputs, A and B. So C is the output of NAND gate. Okay, so here we are having four possible combinations. The first combination is 0 0. Okay, so for this input combination 0 0, the output will be logic 1. Okay, so here you can observe that all the inputs of NAND gate is logic 1, then output is logic 0. Otherwise the output will be logic 1. Okay, so here both the inputs are logic 0, so the output of NAND gate is logic 1. In case of AND gate, what is the output of AND gate for these two inputs? If both the inputs are 0 0, what is the output of AND gate?
Dinesh Kumar and Rizwan type plus 0, sir.
Yes, good. So for AND gate, if you are applying 0 0 on the two inputs, then AND gate produces logic 0 as the output. But here the NAND gate produces 1. That means complement of 0 is the 1. Okay, so NAND gate is complement of AND gate or not of AND operation, right? So the second possible combination is 0 1. For this case also NAND gate produces 1. Okay, third case 1 0. For this third input case, output also 1. But the fourth combination 1 1 produces logic 0. If both the inputs are 1, then output goes to logic 0. Okay, so you can compare these statements and truth table. Okay, you can compare this given statement and truth table. Okay, if all the inputs are logic 1, okay, A and B both are logic 1, then output is logic 0. Otherwise, output will be logic 1. Or you can say that, alternatively you can say that if any one of the input of NAND gate is 0, any one of the input of NAND gate is 0, then output of NAND gate will be logic 1. Okay, so here third combination and second combination. Okay, if you are taking these two combinations, among two inputs, one input is 0. Okay, for this case, output is 1. Similarly, here, the first case, both the inputs are 0, so output is 1. Right? So alternatively, you can say that if any one of the input is, at least any one of the input is logic 0, then NAND gate produces logic 1 as the output. Okay, if all the inputs are 1, if all the inputs are 1, then output goes to logic 0. Right? Then next case is NOR gate. So NOR gate, it means the not of OR operation. Okay, not of OR operation. Okay, so that means OR followed by NOT gate. Okay, OR followed by NOT gate. So this is my input A, then this is my input B, this is my output C. Okay, so OR gate followed by NOT operation, or you can say NOT of OR operation. Okay, so this is nothing but the combination of these two gates gives a NOR gate, right? So in this gate, at least any one of the input of the NOR gate is logic 1. Okay, at least any one of the input is logic 1, then output will be logic 0. Otherwise, output goes to logic 1. Okay. So from this table, you can observe the given statement. So this is the logical expression for NOR gate. C equal to A plus B whole bar. A plus B, this alone represents OR operation. On this OR operation, we are taking NOT operation or complement operation. Okay, so A plus B whole bar gives NOR operation. Okay, so here we are taking two input NOR gate. Okay, here also there are two inputs. So 4 possible combinations. So for first case, 0, 0. If I am giving the input 0, 0, then what will happen? The output will be logic 1. Okay, because both the inputs are 0, 0. So this NOR gate produces logic high. Right? Then second case, 0, 1. If I am applying 0, 1 combination, 0 on the input A, 1 on the input B. For the second combination of input, my NOR gate produces logic 0 at the output. For third case, 1 on input A, 0 on input B. Okay, my output is logic 0. For fourth case, both the inputs are logic 1. For this case also, my output is 0. Okay, from this table, you can observe that this truth table, okay, output column gives inverse of NOR or OR operation. Okay, this output column gives inverse of NOR operation. Okay, in case of NOR gate, what is the output for 0, 0 input combination? When you are applying input, both the inputs are 0, 0, then output of OR gate will be 0, right? But in case of NOR gate, output is 1. That is complement of OR operation. Okay, but for other three input combinations, 0, 1, 1, 0, 1, 1, what is the output of OR gate? OR gate produces logic 1. Okay, OR gate produces logic 1 for these three input combinations. But NOR gate produces logic 0. Okay, it means invert of OR gate. Okay, so from this truth table, you can observe that NOR is not of OR operation. Any doubts so far? So we have discussed AND gate, OR gate, NOT gate, NAND gate, and NOR gate. Okay, so among these 5 gates, is there any doubt?
No, sir.
Okay.
If anybody is
Then
having
we
doubt,
move
you
on
can
further.
type in the chat.
Then logical operation of XOR gate. So XOR gate, here also we are assuming a 2 input gate. If both the inputs to the XOR gate is having same logic, okay, if both the inputs are having same logic, okay, if both the inputs are logic 0 or both the inputs are logic 1, then output, okay, so if both the inputs are same, then output will be 0. Okay, the logic may be 0 or 1, but both the inputs are having same logic. Okay, A and B both are 0, or A and B both are 1. That means then XOR gate produces logic 0 as the output. Okay, otherwise the output will be 1. Right? In other words, you can say that odd number of logic 1 inputs to an XOR gate produces output logic 1. Okay? If the number of ones available in the inputs, that is odd number. Okay? Under this condition, XOR gate produces logic 1 in the output. Right? So this is the truth table for XOR gate. This is the logical expression C equal to A XOR B. Okay? Encircled plus sign represents XOR operation. So C equal to A XOR B. Okay? So if you are applying inputs 0 0, okay, both the inputs are same. Both the inputs A and B both are 0 0. Okay, if both the inputs are same, then output will be 0. Okay, first statement. If inputs are same logic, then output is logic 0. Okay. Then the second condition. If you are applying 0 on the input A and 1 on the input B. Okay, for this condition, output is logic 1. Okay. Here you can clarify just with this statement, this alternative statement. Okay, for odd number of ones, odd number of logic 1 inputs produces logic 1 output. Okay, here they are having 2 inputs, so among them the input B having logic 1. Okay, 2 inputs, on that one logic 1 is available. Okay, that means odd number of 1. So odd number of 1 produces logic 1 as the output. Okay, similarly the third possible combination is 1 on input A, 0 on input B. Okay, here also odd number of 1. So this odd number of 1 produces logic 1. Okay, then fourth combination 1 1. Here we are applying logic 1 on both the inputs. That means both the inputs are having same logic 1. For this case, output will be 0. Right? So XOR gate produces logic 0 when all the inputs are same logic. Okay? Otherwise, it produces logic 1 on the output. Or alternatively, you can say, if odd number of ones are available in the inputs, XOR gate produces logic 1 as the output. Right? Then the next gate is XNOR gate. XNOR. That means not operation of XOR gate. XOR followed by NOT gate. XOR followed by NOT gate. Okay, so here the logic is reversed. If both the inputs to the XOR gate is having same logic, okay, if XNOR gate having same logic on the inputs, then output goes to logic 1. Okay, here the logic is 1. Reverse of XOR operation. In XOR operation, if both the inputs are same logic, then output will be logic 0. But here, output is logic 1. Okay, otherwise the output will be logic 0. Alternatively, you can say that even number of ones. Okay, even number of logic 1 input produces logic 1 output. Okay, XNOR gate produces logic 1 as output when even number of logic 1s are available in the input. Right? So this is the truth table for XNOR gate. Okay, encircled dot represents XNOR operation. Right? So first combination 0 0 produces logic 1 because both the inputs are same logic. Both input A and B having same logic, that is logic 0. In this condition, XNOR gate produces logic 1 as the output. Okay. Then second case 0 1 0 1. Okay. The logics are different on both the inputs, and also the number of logic 1s on this input is odd. Right? The number of ones available in this input is odd. So output goes to logic 0. In the third combination 1 0. Here also both the inputs are having different logic, and also the number of ones available in the input is odd. So output goes to 0. So this is the fourth combination 1 1. Okay. So both the inputs are having same logic 1 1, and also you can observe that both the inputs having logic 1 that produces even number of ones. Okay, the inputs having even number of logic 1. So output goes to logic 1. Right? Any doubt? Any doubt in the operation of XOR and XNOR gate? So simply you can remember that if both the inputs are same, if both the inputs are having same logic, XOR gate produces logic 0 as the output. Okay, but XNOR gate produces logic 1 as the output. Or you can remember the operation of XOR and XNOR gates in terms of odd number of ones, even number of ones. Okay, so whichever convenience you can keep in mind. Any doubt? So shall we move on further? Hello? Ram sir?
They are not typing, sir. Now they are typing. Yes, sir. We can move.
So from this truth table, okay, so we have discussed the logical operation of basic logic gates. Okay, nearly 7 logic gates we have discussed so far. So from that logic gate truth table, so we have some inference. So we can take some inferences from truth table. Okay, first we will consider AND gate. So from this truth table of AND gate, we can observe 2 concepts. Okay, the first one is A dot 0. A dot 0, that is equal to 0. That means if one of the input is logic 0, then whatever may be the input under with that logic 0, then the output will be logic 0. Okay, or otherwise you can say that if you are taking a variable a, with that variable a, if you are ending the 0, okay, a dot 0 will produce logic 0 as the output. Okay, so this is the first inference. So these are all some post case. Okay, we will use these concepts in minimization of Boolean expressions. Okay, in future class we will discuss about that concept. Okay, while discussing about that concept, we will use these kind of inferences that are called as post cases. Okay, then from this input combination, we can observe that the input A having logic 0. Okay, input B having logic 1. That means this 1 is complement of input A. Okay, similarly for third input combination, input A having logic 1 but input B having logic 0, that is complement of input A. Okay, so if you are doing AND operation, these kind of data, these kind of inputs, then what is the output? 0 0. Okay, so A dot A bar, A AND with complement of that variable A bar produces logic 0. Okay, is it clear? Variable and complement of that variable. Okay, by doing AND operation on these two data, you will get logic 0 as the output. A dot A bar produces 0. Okay, so here you can say that if I am taking, for example, A equal to 0, then what is the value of A bar? A bar will be logic 1. So 0 dot 1. Okay, 0 dot 1. Okay, the value of A is 0. The complement of A, that is A bar will be 1. Then 0 and with 1, that produces logic 0. Okay, so this is the second inference from this truth table. Okay, similarly you can also infer something from OR gate. So this is the first inference from OR gate. So here A plus 1, that will give logic 1 as the output. Okay, if the input is logic 1, okay, if one of the input is logic 1, one of the input is logic 1, okay, whatever it may be the second input, okay, the result will be logic 1. Okay, alternately you can say from this table, if you are considering the variable A, okay, variable A having 0 and 1, okay, 0 and 1, okay, but these two cases, the input B having logic 1, okay, for these two cases, what is the output? Logic 1. Okay, so one of the input is fixed with logic 1, then whatever may be the logic level on another input, the output will be logic 1. Okay, so A plus 1 gives logic 1. Okay, then A plus A bar, A plus A bar, okay, A and the complement of that particular variable A bar. If you are doing OR operation on these two data, then result will be logic 1. Okay, for example, if I am considering a logic 0 on the input A, then what is the complement of this input? Logic 1. So 0 OR with 1 will give logic 1 as the output. Okay, this can be observed from this table. Input A having logic 0, input B having logic 1. That means A having 0, B having complement of that input A, 1. Okay, so this combination produces logic 1. Right? Then here actually this may be 1. Okay, because this is a OR gate. OR gate definitely produces logic 1 if one of the input is logic 1. Okay, this here This is not 0, it should be 1. Okay. Okay, now input A having logic 1, but B having 0, complement of input A. Okay, so 1 or with 0 definitely produces logic 1. Okay, so based on these two combinations, we can infer this kind of postulate. A plus A bar, A plus A bar will give logic 1. Okay, a variable ORed with complement of the same variable will give logic 1 as the output. Then from XOR gate, you can infer A XOR with 0. Okay, if you are XORing between A and 0. Okay, if you are taking the variable A, if the variable A is XORed with a logic 0, then the result will be that particular variable. Okay, the variable may be A or B or C. Okay, which is assumed for the particular gate. Okay, if you are doing XOR with logic 0, then output will be that particular variable. A XOR 0 will produce logic variable A. Okay, so this can be observed from this truth table. So here we are taking input A equal to 0, then that 0 is XORed with again 0. Okay, input B having 0, right? So here the output is 0. Here we are assuming A is the variable, then this variable having logic 0, right? Same value, same result is applied in the output of XOR gate, right? So this it can be cleared in this case. So here the logic input A having logic 1, this logic 1 is XORed with logic 0, okay, which is assigned with input B. This combination produces logic 1. Okay, so this logic 1 is available on the input variable A. Okay, so these two outputs are nothing but the input A. Okay, so like that you can observe this kind of postulate. It is one of the postulate. Okay, A XOR with 0 produces the variable. Okay, any variable XOR with 0 will give that particular variable as the output. Right? Then second inference from this XOR gate is, if you are XORing 1 with any variable, okay, if you are XORing 1 with any variable, then you will get complement of that variable. Okay, if I am taking variable A and XORing that variable with the logic 1, then we will get complement of that variable A. Okay, we will get A bar, that is the complement of variable A. Okay. Then we will see some logical operations on binary numbers. Okay, so still now we have performed logical operation on single bits. Okay, we have two inputs A and B, but both are single bits. Okay, having only one value, either it may be 0 or 1. But if these inputs are A and B are multiple bits, okay, say for example 3-bit or 4-bit or 8-bit or 16-bit. Okay, A bit is for example 4-bit, B input also 4-bit. Okay, A and B both are 4 bits. If both inputs A and B are 4 bits, then how can we perform logical operations? Okay, AND operation, OR operations, XOR, XNOR, NAND, NOR. How to do these kind of logical operations on multiple bit inputs? Okay, so we'll start with the AND operation. So logical AND operation of two n-bit binary numbers can be done as follows. Okay, if I'm having n-bit input, okay, here I'm taking input A, that is n-bit in length. Okay, that is n-bit in length. Okay, that can be represented as 0 to n minus 1. Okay, for example, if I am assuming the n value is 4, that is, I am taking 4-bit length. Okay, if I am taking 4-bit length, then how can I represent the bit positions? 4-bit, n is the value of n is 4, then the MSB bit is represented by n minus 1. Okay, the LSB is A0. So I start with A0, then n minus 1. That means 4 minus 1, 3. Okay, so my MSB will be 3. Okay, so we have A0, A1, A2, then A3. So these are the 4-bit representation of the input A. But here we are having n-bit length. Okay, so A0 to n minus 1. Then again, the second input is B. Here also we are considering n-bit length. So B0 to Bn minus 1. LSB is B0, MSB is n minus 1. Okay, so on this n-bit data, we are going to perform AND operation, right? So how to do AND operation? So here we have to perform bitwise AND operation. That means LSB of input A and LSB of input B. A0 AND with B0. Okay, A0 AND with B0. Similarly, the A1 position and B1 position. Okay, so here we will take A1, B1 and will perform AND operation. Similarly, second position, third position up to MSB, right? So here the MSB is A minus 1, B minus 1. Okay, so we will perform AND operation on MSB bits of both A input and B input. Okay, here A n minus 1 and with B n minus 1. So likewise, n-bit binary numbers can be considered for logical operations. When you are considering n-bit binary numbers, we have to do bitwise logical operations like this. Okay, so A0 and with B0, A1 and with B1, A2 and with B2, A3 and with B3, A4 and with B4, A5 and with B5, similarly An minus 1 and with Bn minus 1. Okay, so here the obtained result is also same in length. Okay, the output of this operation will give n bit in length, right? The output also n bit. If you are considering n bit data on input A and input B, then output also n bit.
Selvakumar sir.
Yes, sir.
We may stop here. Time is 12:46.
Okay, sir. Okay. Okay, sir. Okay, so with this, we will stop here. The remaining logical operations on multiple bit binary numbers will be discussed in the next session. Any doubt?